Number 20, looking at the definition of mutually exclusive events, and this is covered in 3.3. And what it means to be mutually exclusive is that the two events cannot occur at the same time. And for this example, our first event is randomly selecting a female history major, and event B is randomly selecting a history major who is 19 years old. And these are not mutually exclusive. You could get someone that falls into both categories and select a female history major who is also 19 years old. Number 21, we're looking at the addition rule, which is what we use for OR probabilities. And in this case, we're finding the probability that a randomly selected carton has a puncture or a smashed corner. And we're still in 3.2 here. And to calculate the OR probability, essentially all we're doing is adding together the probability of each of the two events. And then we want to be careful we didn't double count outcomes. And so we need to subtract away the probability of both events happening at the same time because it would be getting counted in both of these probabilities. So subtract away the intersection, the AND probability of both events occurring at the same time. So in our example, the probability that a randomly selected carton has a puncture, we're going to take that probability or a smashed corner and add it to that second probability, and then subtract away the probability of both of those occurring, a puncture and a smashed corner. So add together the probability of each event and then subtract the probability that they are both occurring. And that gives us our result here for our OR probability. Number 22, looking at some more OR probabilities when rolling a six-sided die. So rolling a 4 or a number greater than 3. The chances of getting a 4 are 1 out of the 6 options on the dice. Numbers greater than 3, a 4, 5, or 6, there's 3 out of 6. So add those two probabilities together and subtract the probability of both, which would be getting a 4 and it's also greater than 3. Well, 4 is greater than 3, so there's one way to do that. You get a 4. So subtract 1/6. So doing that leaves you with 3/6 or 50%. Rolling a number less than 4 or an even number for part B. There are 3 numbers less than 4, so 3/6 plus there's 3 even numbers, so 3/6. And then both, the only number less than 4 and even is the number 2 on the dice, and so there's 1/6 is the probability of getting a 2. So subtract that probability, add those all up, you get 5 out of 6, and then do 5 divided by 6 to convert it to a decimal probability. And you can see the problem has it written out here nicely. You can think about getting a number less than 4 or an even number. What all options would that be? And it's getting a 1, 2, 3, 4, or a 6. And that's 5 out of the 6 options. And that's what we had. 5/6 is our probability. Part C is rolling a 2 or an odd number. And they just have the 2 and the odd numbers written out. So it's 4 out of 6 or 2/3. And then this is it as a decimal. And then looking at it with the addition rule, the probability of getting a 4 is 1 out of 6. The probability of getting an odd number is 3 out of 6. So we would add those two probabilities together and then subtract the probability of both of them happening, which is in this case 0% because these are mutually exclusive events. You can't have a 4 and it be an odd number. So doing that addition here, we get 4 out of 6, which is our same result over here as a decimal. Number 23, we have a table of results from a survey. And I want to copy that into Excel to get these numbers. And we have some OR probabilities here. Find the probability that a person is frequently or occasionally involved in charity work. So the probability someone is frequently or occasionally involved, the probability of frequently would be the number that are responded as frequent over the total people in our survey, and add that to the number who were occasionally engaged over the total, and then subtract anybody who is both, and you have to be one or the other here. These are mutually exclusive, and so we would be subtracting 0 and reduce that down to get our probability. Next part, find the probability that a person is female or not involved in charity work at all. The probability that someone's female would be the number of females over the total survey responders. Not at all, look at that column, there's this many out of the total. And then we add those together, but we need to subtract the probability that someone is both, which in this case would be that they are female and not involved at all. And there were 749 out of the total would be the probability that someone is both. So do this addition and then subtraction to get the OR probability here. Part C, the probability that our randomly selected person is male or frequently involved. So calculating our OR probability, the males out of the total, that probability plus the number of frequently involved people out of the total, add those together and subtract the probability that someone is both, which in this case, the males who are frequently involved out of the total. And part D, the probability that a person is female or not frequently involved. The probability of being female, you would take the number of females out of the total. That's the probability of being female. For not frequently involved, that probability takes a little bit of math here because we only have the total for frequently. For not frequently involved would be every other person. So we need to take our total and subtract the number who were frequently involved, and that gives us the total who were not frequently involved. And you can also get that by adding together the totals from the other columns. And so that's the probability of being not frequently involved. Add those two together, but subtract anybody who is both, which in this case would be a female who is in a column here besides the frequently involved column. So if we add those two together and put that result over the total, that would be the probability of someone being both female and not frequently involved. So as we reduce this down, we will get the probability, the OR probability that we're looking for. Number 24 is asking about the definition of a discrete probability distribution. And this is discussed in 4.1. To be a discrete probability distribution, there's a finite countable number of possible different outcomes and values the random variable can assume, and each of those outcomes has a probability associated with it. All those probabilities have to be in between 0 and 1. Probability is always a value between 0 and 1. And then the sum of all the different probabilities has to equal 1. And as a decimal, 1 is equivalent to 100%. So all the different probabilities sum up to 100%. Number 25 is emphasizing the point that in most scenarios and applications, discrete random variables represent counted data. An example would be, how many pets does the average household have? That's something you can count, either 0, 1, 2, and so on. While continuous random variables represent measured data. An example would be, what does the average Labrador dog weigh? You would have to measure that using a scale. Number 26, we have a frequency distribution here for overtime hours worked, and we're going to start by constructing a probability distribution. So I'm going to copy this into Excel. So this is a discrete probability distribution. The only possible outcomes are listed here, either 0 overtime hours up through 6. To find the probability of a randomly selected person falling in any of these categories, first we need to know how many total employees we have. There's 190 data points here in our frequency distribution. So for each one of our different options here, I want to take the number that fall into that category. So there's 7 people who worked 0 hours and divide by the total. Now I'm actually, instead of writing 7, going to write B2. And so it's doing 7 divided by 190. And that's the probability that if I randomly select an employee, they will work 0 hours of overtime. Now the reason I wrote B2 is because now I can drag this down, and the next one will do B3, B4, and so on. And this is 11 divided by 190, and it's the probability that a randomly selected person works 1 hour of overtime, and so on. So you get the complete probability distribution here, and you can verify these should add up to 1 or 100%, because we have the probability for all the different possible options. The next part is to choose a graph of our probability distribution. So the x-axis is going to be the different possible outcomes, 0 through 6. And then the height of each bar should match up to the probability associated with each of those different outcomes. Excel can create that probability distribution for you. If you select your probability column here and go to Insert and just insert bar graph, you're going to see it. Now I don't have my labels right for my x-axis because I didn't select any, but you see that shape of what the distribution should look like, and the height of each bar is correct. This first bar is with the 0 hours of overtime, but Excel just did default labels of 1 through 7, so you would need to go in and change your labels there, but you see the correct shape here. And this is looking pretty symmetric. It doesn't have perfect symmetry on the right and left, but it is approximately symmetric. Something like this would be skewed to the left because it trails off to the left. Something like this here, we would call it skewed right because it trails off to the right. And then for uniform, a uniform distribution is the same all the way across. It's uniform. It doesn't change as we look at it left to right. So skewed right, skewed left, approximately symmetric, uniform. For number 27, we're using the definition of an unusual event being something that has less than a 5% chance of occurring. And we're asking if it would be unusual for a household to have no HD televisions. So here's a discrete probability distribution. The probability of a household having 0, 1, 2, or 3 is listed. Right here, the probability of each of those outcomes. So the probability of having 0 is 0.03 or 3%. That's less than 5%, so it would be unusual.